Speeding at Sea, it's me Z, and welcome to the long-awaited PDEs course by yours truly. This was all made possible thanks to you guys for raising over 2.5k for LA wildfire relief. Thank you all so much. Before I get started, I did want to mention that PDEs can be scary. It was challenging when I first learned it too. That being said, don't hesitate to drop questions in the comments below, and I'll try to get to as many of them as possible. And of course, don't forget to like and subscribe to see more of these series. Now, before we get into partial differential equations, the big leagues, the mathematics behind waves, heat, quantum mechanics, financial options pricing, everything, we need to understand how to solve ordinary differential equations, or ODEs. So, a speedy intro to solving most types of ODEs in just one video. Let's get started. Solving ODEs is a very methodological process, and in most cases can be as easy as identifying what type of differential equation you have and putting the solution in the correct format. Now let's start with the very basics, first order ODEs. Now the word first order refers to the fact that the derivative is being taken only once. For instance, a very common type of first order ODEs are called separable ODEs, and they are of this form: dy dx is equal to g of x, h of y, where g is a function of x and h is a function of y. You commonly see these in cases of radioactive decay or cooling. Now, these are called separable ODEs because you can actually separate them into two parts. You can move the component that's dependent on y to the left and the components that are dependent on x to the right. And then all you have to do next is to integrate both sides and solve for y. Now this is a very simple case, but what happens when we have instances that are not necessarily separable? For instance, we can actually encounter an ODE that looks something more like this: dy dx plus p of xy is equal to q of x. In this case, we actually have an integrating factor. If we see an ODE of this form, the first thing to do is identify what is that p of x term. And to solve this ODE, you simply have to define the integrating factor in this form shown here. And solve for y with this equation. 1 over mu of x, where mu is the integrated factor, times the integral of mu of x times q of x dx. You commonly see these in cases where you're dealing with RLC circuits and so forth. So in both of these cases, what you need to do is simply identify the form that the ODE is in, and then put it into the correct format and solve for y. But let's say we have a more complex case. After all, most instances in physics, you would actually encounter dependencies of the second order. And more specifically, these equations can be of the form y double prime plus ay prime plus by is equal to 0. We see these in cases of a ball flying through the air. We see this in cases of a mass oscillating on a spring, or the changing current over time in a circuit. This is more specifically called a linear homogeneous ODE. Now, in my next video, I'll go into more detail about what it means to be linear and why that is important. But the reason why this is called homogeneous is because there is no dependency on x other than through y. More specifically, the back half of this equation here is simply equal to 0. So how do we solve for y in this more complex case? Well, we have a double derivative here, and we have all these different terms. It seems to be almost impossible to separate this out. Well, I can actually simplify this into just 3 or maybe even 4 easy steps. So let's go through this real fast. Step number 1, get the characteristic polynomial. So you have an equation of this form, right? A y double prime plus a y prime plus by is equal to 0. The way that you can find this characteristic polynomial, which will become central to how we solve ODEs moving forward, is by converting this into lambda. So this becomes lambda squared plus a lambda plus b is equal to 0. And if you look a little closer, you can see how this conversion took place. Because there's a double prime here, a double derivative, this actually becomes squaring in the characteristic polynomial. There's one derivative here, so that becomes 1 lambda. And in this case, there are no derivatives, so this actually becomes a constant. And this characteristic polynomial is going to be very, very central. Because the next step is to solve for lambda. And this is just a typical quadratic that you would deal with, a parabola, or it might not even necessarily have real solutions, but let's just draw it like this. And we need to solve for the 2 solutions, lambda 1 and lambda 2. And we can do that with the quadratic formula or by factoring. Now, the step number 3 is to identify which format you have for the ODE. Now, this is where things get a little bit more complicated. It depends on the solutions that you got for the characteristic polynomial. So when you get lambda 1 and lambda 2, there are a few formats that you could encounter. For instance, you could say that lambda 1 and lambda 2 are distinct, aka different, and real. In this case, we would say that the solution to this ODE is of the form y of t is equal to c1 e lambda 1t plus c2 e lambda 2t. So what is exactly going on here, right? c1 and c2 are constants. They're numbers like 1, 2, 3, or in some instances even more complex than that. Lambda 1 and lambda 2 are the solutions to the characteristic polynomial that we just solved. The second instance that you could encounter is that lambda 1 and lambda 2 are imaginary. So in the previous slide, I showed that the characteristic polynomial can be drawn like this, where there are 2 solutions on the x-axis. But of course, we could encounter characteristic polynomials that are above the axis. In that case, those solutions are imaginary. And when these solutions are imaginary, we say that lambda 1 and lambda 2 can easily be described in the form r naught plus or minus s naught I. So this is a constant. It can be both of these are constants. They can be numbers, 1, 2, 3, etc. Any real numbers. But this is unique in that it has this real component, r naught, summed up with this imaginary component here. And by putting lambda 1 and lambda 2 into this given format, we can then identify the solution to the differential equation into this format. Y of t is equal to c1 e r naught of t cosine s naught of t plus c2 e r naught of t sine s naught of t. So it's really just as simple as what are the solutions to the characteristic polynomial and how can we simply insert them into this format. But of course, we're not done yet. The final instance that we could deal with is if lambda 1 is equal to lambda 2. In this case, if we draw the characteristic polynomial, that one doesn't necessarily have to be 0. But let's say that there is just one solution along the x-axis. In that case, we would say that the solution to the differential equation would be c1 e lambda 1t plus c2 t e lambda 2t. And those are all the cases we could deal with. Case 1, when lambda 1 and lambda 2 are distinct and real. Case 2, when lambda 1 and lambda 2 are imaginary. And case 3, when lambda 1 is equal to lambda 2. Now, that was a lot of information. And of course, it may also seem like a lot of memorization. But let's actually work through an example. Let's say that we have the ordinary differential equation y double prime minus 2y prime plus 3y is equal to 0. Now note that we are dealing with homogeneous differential equations. That's why this side is equal to 0. So let's start out by solving it. Remember step 1, right? Do the characteristic polynomial. We recognize that there is a double derivative on y, so we do lambda squared minus, there's one derivative on y here, so 2 lambda, plus there's no derivatives here, so we get 3 is equal to 0. This is our characteristic polynomial. Step 2, solve for lambda. It seems like this is an imaginary solution, but fortunately, we have the handy-dandy quadratic formula. The quadratic formula is negative b plus or minus the square root of b squared minus 4ac all over 2a. I still use that quadratic formula song. But when we solve for lambda, we're going to get this really funky equation here. And what you may notice is that there's a negative number under the square root. That's still allowed because, as I showed before, we can have imaginary solutions. And when we divide out the top and the bottom, we'll get 1 plus or minus square root of 2i. So, step number 3. Identify which format you need for the solution. This is an imaginary solution, which means that we need to first put lambda 1 and lambda 2 into the format r naught plus or minus s naught I. And our final solution will be of this form. Now, this is pretty comparable. These look very, very similar. So when we put these two side by side, we can actually see that r naught is equal to 1 and s naught is equal to square root of 2. And so when we're actually able to assemble the solution together, we simply plug it in to this template we have right here. So we get y of t is equal to c1 e of t cosine, and we said s naught was square root of 2, square root of 2t, plus c2 e of t sine square root of t. And that is the solution to our ordinary differential equation. So let's work through maybe a few more rapid fire examples. Let's say we have the ODE y double prime minus y is equal to 0. So step 1, again, solve for the characteristics polynomial. So we have a double derivative here, lambda squared, minus no derivative here, 1 is equal to 0. In this case, we have real solutions. We have lambda is equal to plus or minus 1, and they are distinct and real. Step 3 was to identify which format we need. Well, because we have distinct and real solutions, we can say that the solution falls under the format c1 e lambda 1t plus c2 e to the lambda 2t. But we said that lambda is equal to plus or minus 1. So lambda 1 is equal to 1, and lambda 2 is equal to negative 1. And without loss of generality, we can basically switch lambda 1 and lambda 2 in this instance. And finally, the next step is to simply plug that into our template. So lambda 1 was equal to 1, so we have c1 e to the t plus c2, and lambda 2 was equal to negative 1, so we have e to the negative t. And that's the solution to our ordinary differential equation. Now, of course, I mentioned that there could also be a fourth optional step. In some instances, you can actually solve for the constants C1 and C2 if you're given an initial value problem. In that case, you're given some sort of starting point. Let's say we can say y of 0 is equal to 1. And what you would do is plug that into the ODE and solve for the constants C1 and C2. Now, of course, so far, we've been dealing with a very, very specific type of ODE. We've been dealing with homogeneous ODEs. Or are they pronounced homogeneous? I learned it as homogeneous, but I think they're actually pronounced homogeneous. Well, anywho, we dealt with ODEs of this form. And we said they were homogeneous or homogeneous because there was a 0 at the end. Now, in most cases of physics, this isn't necessarily true because there could actually be another function here that's dependent on time. For instance, the equation for a damped spring mass system can be described as my double prime plus cy prime plus ky is equal to p of t. And this is also known as the forcing function. In fact, there's actually a lot of different examples of this forcing function coming into play. You may have also encountered, if you're in electronics, an equation that looks something like this. What's going on here is that it's solving for the current I of a circuit with RLC components when dealing with a periodic voltage source, which we see here as the cosine dependent on time. And so we now have to introduce a new type of ODE, inhomogeneous ODEs. Which are of this form, y double prime plus ay prime plus by is equal to f of t. And more specifically, these are second order ODEs because the maximum derivative here is to the second derivative. So how do you solve these? Well, fortunately, we don't have to completely scrap everything that we just learned. The easy templates or just identifying what the characteristic polynomial is. In fact, all we have to do is add a few additional steps to deal with this forcing function. Step number 1, or method number 1, is called the method of undetermined coefficients. I definitely need to work on my handwriting. And you use this in cases where f of t is nicely formatted. Now, what do I mean by that? Would I be able to encounter a forcing function and be like, ah, yes, that one looks very, very attractive and would definitely be nicely formatted? Well, no. And also, yes. You typically see these in cases where you have a sine, an exponential, a constant, and so forth. Functions that are basically described by just one thing, maybe like e to the t, or maybe sine to the t. And in fact, there's actually a whole table of them that I will paste around now that you can use as a reference as to when you can actually use this method. Now, one of the examples that might be the easiest to show is when you encounter a forcing function of the form k e to the at, where k is a constant. You can actually guess what the form would be in the solution to the ODE. And in that case, you would guess that the form would be of the form a times e to the at, where a is also a constant. So let's work through an example where I can sort of show you how exactly this forcing function comes into play. So let's go back to our previous example except this time, instead of 0, we have 3e to the 5t on this right-hand side. Now, don't worry, everything actually remains mostly the same. So from our previous solution, we already solved for the characteristic polynomial, solved for lambda, to solve this part on the left-hand side. And all of that remains the same. Now, all we have to do is deal with this right-hand side. And we can use the method of undetermined coefficients. Because this is of the exponential form, we can say, let's guess that the solution will look like ae to the 5t. And what we do next is that we substitute this expression back into the original equation here on the left. So we say that our guess for the forcing function is ae to the 5t. And let's do the derivative of that so that we can substitute it in later. And let's do the derivative once more here. And now all we have to do is plug it into here on the left-hand side. So we plug in the forcing function and its derivatives into here. So then we get 25a to the 8 times e to the 5t, which is the forcing function to the second derivative, minus 2 times 5a to e to the 5t, which is the first derivative of the forcing function, plus 3 times ae to the 5t, which is no derivative on the forcing function. And we know that that must equal to the right-hand side. So now we have this expression here, which means we simply have to solve for this constant a. So in order to do that, let's actually first take out a. And then we get this expression here. We can then simplify this even further to get 18e to the 5t, which is equal to 3e to the 5t. And what we need to do next is we can simply divide out the e to the 5t and solve for a, and a is 1/6. Now what do we do with this information? We've finally done a guess, and we figured out what the constant is associated with that guess. Well then, there's no other tricky method. All you need to do now to find the final solution is that you add the original solution that we got up here, and then you just have to add the guess from the method of undetermined coefficients. We said that was of the form ae to the 5t, but we already solved for a, and a was 1/6. And so our final solution is then just what we solved for on the left-hand side plus what we got on the right-hand side. Now, the official word for this expression here isn't just the guess, although that would be really, really fun to say. But it's officially known as the particular function, which is also a very admirable name. And so by summing up what we got for the homogeneous case with the particular function, we then completely solved for the inhomogeneous ODE. Now, what if our ODE has a right-hand side that looks absolutely ugly? Well, in that case, we got to use the method of variation of parameters. Although this name does sound a little bit long, I do promise you that it is fairly straightforward. It just involves a few integrals to solve. And what's even greater about this method is if you encounter the right-hand side being a funky one and thinking, oh, I don't know if this fits into a particular template for me to use the method of undetermined coefficients, then this method of variation of parameters works in all cases. It is a general solution, although it takes a lot longer than the method of undetermined coefficients. So now let's say you have a solution of this form. This is very similar to what I showed before, except now I've replaced a and b with q of t and r of t, and this is our forcing function g of t once again. Now, if we found that the solutions to this left-hand side, the homogeneous ODE, is y1 and y2, then the particular solution, the little bit that we have to add on after we solve for the homogeneous case, is written as this crazy expression, negative y1 times the integral of y2 g of t over the Wronskian, which I'll describe a little bit in a second, plus y2 y1 g of t over the Wronskian once again dt. Now the Wronskian sounds like an incredibly scary term, but it's simply described as y1 times y2 prime minus y2 prime times y1. And this expression has to do with the way that you determine properties of a matrix. Now, with this crazy expression, let's go through a full example. Let's say that we have the expression 2y double prime plus 18y is equal to 6 tangent 3t. Now, when you first look at this expression, you can say, oh yes, this side on the left is the homogeneous ODE. We can solve for that using the characteristic solution like we always have, the characteristic polynomial. Now, when you look at the right-hand side here, you might be thinking, oh my god, that is a tangent function. How in the world will I be able to deal with that? Well, thankfully, we have the method of variation of parameters to help us out. But first, let's not jump the gun, and let's first solve the left-hand side. The homogeneous ODE. Again, let's go through the steps. Step number 1, find the characteristic polynomial. There's a double derivative on this one, so 2 times lambda squared plus 18, but there's no derivative on this one, so we put that as a constant, and we set that equal to 0. Now we got to solve for lambda. We can actually move this 18 over to the right-hand side. And from there, we see that lambda squared is equal to negative 9, which means we're dealing with imaginary solutions. So lambda is equal to plus or minus 3i. But don't worry. Remember, this is step 2 where we solve for lambda. Step 3 is to identify the template. We have an imaginary solution here, which is of the form r naught plus or minus s naught I. In this case, r naught is 0, and we see that s naught is 3. So that is equal to plus or minus 3 naught I, which is r lambda. Then we just have to put it into the correct template. Y of t is equal to c1 cosine 3 of t plus c2 sine 3 of t. So this is our homogeneous solution. Now, the next step is to actually solve for that crazy funky bit on the right. So let's walk through the method of variation of parameters. So first we need to identify what is y1 and y2. Well, one big misconception here is that this would just be equal to the lambda we solved in the previous step, which would be plus or minus 3i. That is not the case. y1 and y2 actually refer to the different parts of the solution that we found for the homogeneous case. So we said that y of t is equal to c1 cosine 3t plus c2 sine 3t. And so from here, we see that y1 is equal to cosine 3t and y2 is equal to sine 3t. We actually drop the constants when we write y1 and y2. Next up, we got to solve for the Wronskian. Now, of course, this sounds really scary, but don't worry. We know that it's just equal to y1, y2 prime minus y2, y1 prime. And so we can solve for the derivatives here to get negative 3 sine 3t, and y2 prime is equal to 3 cosine 3t, and plug it into this expression for the Wronskian. So first we have y1 is cosine 3t, we have y2 prime is 3 cosine 3t, we have y2 is sine 3t, and y1 prime is negative 3 sine 3t. And putting that all together, we get 3 cosine squared 3t plus 3 sine squared 3t. But you may notice that this is actually a very famous identity. Cosine squared of anything plus sine squared of anything is equal to 1. And so this expression, when we take it out, is simply equal to 3. Now we're not done just yet. We've just gotten one of the components we need to solve that crazy integral that we saw in the previous slide. Remember again that the solution can be written in this form. Now all we need to do is combine all of the different parts. So we have the Wronskian. We said that the Wronskian was 3. Very simple, very easy. We said that y1 was equal to cosine 3t. And we said that y2 is equal to sine 3t. And now remember that g of t refers to that forcing function, which we said was the crazy 6 tangent 3t. So all we need to do next is substitute everything into this expression. All we got to do is plug and chug. So negative cosine 3t times integral of y2 times 6 tangent 3t over the Wronskian, which was just 3. So that is this expression here first. Then the second expression, sine 3t to the integral of cosine 3t times 6 tangent 3t over 3 dt. And that is our particular solution. Now this is absolutely crazy and still looks absolutely abysmal to solve. But fortunately, we have things like Wolfram Alpha and Integral Calculator that can help us. And before this, I actually went in and actually plugged it in to see what we would get. And what we get is this even crazier expression. Now, there is no way that we could have solved this using the templates in the method of undetermined coefficients. This would have only been possible using the method of variation parameters, but this is the particular solution that we get. Now, after this, do you remember what we have to do next? Well, there's not much more to add to it. All we need to do is sum up the homogeneous solution with this particular solution here. So, if we go back, we know that the original homogeneous solution was C1 cosine 3t plus C2 sine 3t. And after that, we just need to add this to the end. Negative cosine 3t over 3, natural log of secant 3t plus tangent 3t with an absolute value. And all together, that is the final solution to the ODE. 2y double prime plus 18y is equal to 6 tangent 3t. And that's ODEs, a super speed run version. Now, of course, with this, we covered a lot of different things. From the separable first order ODEs that we saw at the very beginning, to using the characteristic polynomial and matching the different templates to their solutions like we saw with the homogeneous ODEs, and finally, solving for the sometimes crazy particular solutions with the inhomogeneous ODEs and simply slapping that on back at the end of the homogeneous solutions. Now that was a very quick dive into ODEs, and I don't expect everyone to be like, ah yes, I'm an ODE expert after this video. But I hope you learned something new and delved into the world of ODEs, and especially as we further dive into the physics behind these crazy math equations and why they are so powerful. So until next time, if you enjoy this video, please click that updo button And definitely let me know in the comments if you have any feedback, questions, suggestions, or overall general excitement about the next videos in this series. And until next time, I shall see you guys later. Bye bye!